Yeah, right. Oh, yeah. Oh, yeah, you're right. I guess they had to come up with a new one. All right, so what we're going to do today is, so can you turn on the recording for the midterm? Because I don't want the solution for the midterm to be recorded. So what we're going to do today is I'm going to distribute back the midterm pattern. Then we are looking at the average of the class for the letter grade for the course to be about A-. Of course, some of you will get A, some of you will get B+ or B, but most of you will be in the B and above range. And many of you will be A- at least. Some of you will be B+, and some of you will be B, some of you will be A-, but most of you will be in this range. And quite a few of you will be in A range as well. We have 300, that's excellent. 3 of you scored 100 in midterm, which is excellent. Okay, make no mistake whatsoever. Perfect solutions. So that's about midterm. Any question on this? And another comment I like to make is on midterm, if you look at the midterm, the way the midterm was constructed, it's basically the same material you have seen from your homework and lectures. So we're gonna continue the same fashion for your final test. We're gonna be using the same open book policy, and the final problem will be based on homework 3, which is just released today, and homework 4. There will be one more homework. That's about it. So final will be based on those 2 problems, and the lecture we have covered after the midterm, meaning that for the final test, you don't have to worry about anything that's already been tested for your midterm. Okay? Questions? No? Okay, let's continue with our lecture. And remember to return your midterm back to me at the end of the lecture, right? I think this lecture, one lecture time is sufficient for you to go over it, but if you think you need more time, you can always stop by my office hour to check your midterm with me. Okay? So I think we're almost done for career evaluation, right? The only point I want to make is one thing we haven't talked about is the refinement of sort merge. Remember, the basic version of sort merge is that so the basic version of this algorithm is you sort R, sort S, then you join R and S. And while you join R and S, you use this, you skip an entire session from one table if you don't find a matching session from the other table that have the same value on the join attribute. Remember this color table example I used in my discussion, right? Green region, blue region, black region. If you don't find a black region from the other table, you can skip the entire black region of this table, right? But if you find a black region from table R and a corresponding black table from table S, you do a in-memory, you bring both segments to memory, you do an in-memory join using whatever algorithm you choose. You can do a nested loop join, or as Tanya and others discussed on the discussion forum, you can build an in-memory hash table and do an in-memory hash join as well, right? For that black versus black segments. Yes?
So when you're implementing this, to be able to skip over the regions,
yes.
you can just usually store those as a like linked list, so then you know where the next one starts. To scan the whole region.
I see what you're saying. So after the sorting, if you know this is what you want to do, yes, it will be useful to have some facilitating structure so that you can quickly jump to the start of the next region instead of going through each region linearly, as what Dylan had indicated in his question. You follow me? So for example, if this is the red region and this is blue region of one table, and the other table is supposed to be the green, followed by blue. You know there is no, if you are here, on this table, and you are here on this table, and you realize there is no matching green session from table R, so you want to move this cursor quickly to here, to the start of the blue region. If you don't have any facilitating structure to do that, you will have to linear scan the entire green region to bring your cursor to the beginning of the blue region, right? Does that make sense? Which can be costly, especially if you do this in the external memory model. So what Dylan was saying is that after the sort of R and S, in the final merging phase of the sort, external merge sort for R and S, you use some facilitating data structure to remember the start address of each region so you can quickly jump from here to here. And how you do that, there are many different ways of doing that. I don't want to dictate how you do it, but the general idea is you want to have some kind of facilitating data structure for you to jump to the start of each region very quickly. That's what Dylan is saying, right? Is that right?
Yeah.
Okay. Which is a really nice comment, by the way. Okay. So nevertheless, even with this idea that Dylan had proposed to improve the performance of this algorithm, you still have to do the sorting of R and S respectively and do a linear scan over R and S in the final phase. Does that make sense? So the total cost is still considerably higher than the hash join cost. The hash join, the cost is simply this, right? If there's a big if here, if each partition of R or S, the smaller one of the two, can fit in your memory size, right? What we said last time, if you remember, the condition is subject to that the memory size must be bigger than what? The minimum of R divided into how many partitions? R is divided into this many partitions. Sorry, minus 1 for the input buffer. Right? That's your memory size. You reserve one of those pages as your input buffer. The remaining are output buffers, so you can build these many partitions. If you have a perfectly balanced distribution, the entire table of R is distributed into this many partitions, so the size of each partition is exactly this. Similarly, the size of each partition of S is this. In order to do the hash join in just hash partition and rehash space, this condition must be true. So that in the second phase, while you join partition by partition, one of the two partitions from R or S must be small enough to fit in memory so that you linear scan over the other partitions. You follow what I'm saying? A quick recap of what we said. This is your memory. Suppose this is the R partition, this is the S partition. One of the two must be small enough to fit in memory so that you linear scan through this partition and do the join. Right? That's the idea of hash join. Do you follow what I'm saying? Okay? So you have to have this condition. So this cost, if you think about it, in most cases it's going to be much less than this cost. Right? This part is linear, which is R plus S. Assuming each region is small enough to fit in memory again. Right? But you still have to take the sorting cost.
I thought you said with, maybe I got confused, but I thought with hash equal join, I thought that was the one where you hash both of them.
You hash both of them, you hash both of them independently, so that each is partitioned into multiple partitions. Then in the second phase, you join partition by partition.
Okay.
Right? Because the reason you can do that is if a particular value of R, all the records with those values end up in partition 1, then all the records of S having that value must be in partition 1 of S as well.
Okay, so fitting into memory is after you've done that.
After you've done that, yeah, exactly. What you said is combining the partition and hashing fit, that's for the group by aggregation. That's called the hybrid hashing. But that's for group by aggregation, not for a join. Right? So that's a quick recap of what we said. So essentially this is the cost for the sort merge join. If you are doing this, sort, then join, right? The question is, can we do better? Can we do better? Can we, remove the gap between hash join and sorting-based join algorithm? Well, in some cases you can. This is the refinement of sort merge join. I will briefly talk about this. So the idea is as follows. The idea is instead of sort R, then sort S, then join, you can merge or combine the sorting phase with the join operation. So the basic idea is as follows. The setup is you have this is your memory of M over B pages. Right? M over B pages. B is number of objects you can fit in one page, M is total number of objects you can fit in your memory. So your memory size is simply M over B. Right? I hope by now you understand the notation of B and M and so on and so forth. Right? So I'm gonna virtually divide my disk space into two parts. This is the R and this is the S. And this is the disk. So this is my disk. And R obviously has multiple pages. And S has multiple pages as well. Right, so that's essentially your picture. That's essentially your picture. Right? I'm gonna assume that these are already within each page. I'm gonna assume it's already sorted. That's fine. I mean, if not, you bring them in and while you read each page into the input buffer, you sort it. That's not a big deal. Does that make sense? So what you're gonna do is you're gonna divide your memory space virtually into two parts. And there's one output buffer. Do you follow me? Now, the upper section is reserved for pages from R. The lower section is reserved for pages in S. Now, look at the upper section. How would you do the external merge sort algorithm? How would you do the external merge sort algorithm? Well, you have one input buffer for each run. Right? One input buffer for each run. And you load the first page of every run to the corresponding input buffer. And suppose you have enough number of such input buffer pages to represent every single run of R. But initially, each page of R is a run by itself. Right? So essentially, you load every page here. Do you follow me? Argument? Now, in the general case, suppose, let me show a general case. Suppose I have, this is a run, and this is another run, and this is another run. Then the picture is as follows. You load the first page of each run into a corresponding input buffer. You follow me? Right? In the general case, that's what it looks like. And suppose, it's similar here. So within each run, it's obviously sorted. Right? Sorted. Now, same thing here. So stop me whenever you have questions, okay? So far, I think we all understand what's going on, right? This rectangular box represents a run. So within each run, pages are sorted. This is the run for R, this is the run for S. And I virtually divided my in-memory pages into two parts as well. And I'm going to bring the first page of each run into memory. And now I essentially think about this. You are running two sort merge run algorithms, not sort merge run, external merge sort algorithms independently at the same time. You're running two instances of the sorting algorithm at the same time. One for R, one for S. You follow me? You all know how the external merge sort works, right? Just you just start merging them. You move these cursors and in order and push elements to the upper buffer. So to be precise, you're supposed to have two upper buffers. If your objective is to sort them, but your objective is not to sort them, your objective is to join them. Now, so you're gonna merge these two upper buffer into just one upper buffer. You get rid of them. Can someone, I think by this point it should be pretty clear what you do. Can someone tell me what you should do if your objective is to join them? Yes.
So I guess my guess is that you look at, like you pick one from R, and pick one from S.
Yeah.
Or I guess maybe you don't have to pick one, but you merge them at the same time like you would, kind of pretending like they're one giant table to sort. And if you do have two that match the join condition, then you can combine those records. But you have to keep, if they don't match the join, then you have to keep them around in case it matches later, right?
That's the key part. The last part of what you said is important. Because if we have to do that, this algorithm will become super expensive because you have to keep things around and blah, blah, blah. It becomes super complicated. The key point is, if I have a representation for every single run of R, and I have a representation for every single run of S, then I don't have to keep them around. If they don't join now, they will never join.
But how do you know, I guess, that when you're looking at them, that you just haven't read in from S?
So let me explain that in detail, right? So the basic idea, let me repeat the first part of what he said. You look at these cursors. Each cursor represents a record with a particular value of, the value, of course, is the value of interest, like you join attribute. And you compare, for example, this value against all these cursors from S. Some of them will be smaller than this value, some of them will be larger than this value, some other will be equal to this value. Those who equal to this value are exactly the join pairs that you have identified, and you should push them to the output. Basically, you pair this record with all the cursors that have equal values on S, and you push them to output. That's your join pair. Do you follow me? Yes.
Isn't that only on, like, if you're doing an equality join? What about like a gradient?
We focus on equality join.
Okay.
So far, so good. What about those smaller than this value? Why you ignore them? Since this is the first page of each run, and this is the first cursor, if you actually identify a value here that's smaller than all these cursors, what does it tell you? It will never join with any record of R. Even though I haven't looked at the remaining pages of R, if you are smaller than all these cursors, the value is pointed by these cursors, you're gonna be smaller than all the remaining records in the remaining pages that haven't been brought to memory. So you never need to worry about it. That's the idea. Of course, on a condition, which is you must have a representation for each run. If I have a run here from R that's not represented here, and you find a cursor from S onto a value that's smaller than all the current cursors, you cannot safely ignore this record yet, because maybe I have a value here that's smaller than all of this and match exactly the cursor from S. However, if you do have a representation for every single run from R, this will never happen. So the importance of this algorithm is that you must have a representation for every single run of R. Similarly, using a symmetric argument, you must have a representation for every single run of S. When that happens, you just keep merging and joining. And ignore those who are smaller than all the cursors from the other side. And keep moving cursors forward. And whenever you exhausted all record from a page, what do? You bring the next page from the same run, you continue. There's no trick. Yes?
So I guess then do you just have to, until you start like the merge phase, do you just kind of do an initial sort and keep combining rounds until you get enough in memory?
Very good question. So what you're saying is where those rounds come from, right?
Yeah.
I mean, you can do the initial, you can even use the hashing to do this. You hash to different partitions, you sort each partition. That's linear cost anyway. Or you just run the initial phase. the first phase, which is on average produce this many pages in each round, right? The two-element sort. Or to give you size of each one. Do you follow me? In the first phase, right? Or even if you don't use the two-element sort, you use the most naive sorting algorithm, the size of each one is already M over B. At least you bring these many pages, you sort them. That's a one. Then you start doing this. Yes?
So this one, like the original external sorting algorithm we used, we kept doubling the size of each run until we got one run basically.
No, this has
one
one
run,
run, right? You're done, right? You're done. You just keep moving cursors. By the end of exhausting all the runs, you're done. You're done with the drawing. So how do I translate that condition, which is every single run must have a representation in main memory? How do I translate that? Well, essentially, this is M over B minus 2. This is M over B minus 2 pages, right? Pages. Do you follow me? Right? So this must be larger than the number of rounds you have. How many pages you need here is, this is the total number of pages you have, right? Do you follow me? And this must larger than the number of rounds you have for R. Similarly, this must be larger than the number of rounds. Or to be precise, M over B minus 1 must greater or equal than total number of rounds. Because this virtual line doesn't have to be, you can draw the line something like here, if R has more rounds than S, right? You don't have to divide your memory evenly between R and S. So the condition is M over B, the memory size, the total number of pages minus the width that output buffer, must greater or equal than the total number of runs from R and S. That's it. Because you only need one page to represent each run. You only need one page to represent each one. As long as this condition is true, you can do this in one phase. You need, like my earlier response to Dylan, you need one more phase to produce these runs, which is linear cost to R and S. You follow me? Yes? To produce these runs, what's the cost to produce these runs? One phase, right? You need to read R once and write R once. So the total cost to produce these runs is 2 times R plus S. You read them in, you sort them. No matter how many runs you produce, it's linear cost, 2 times goes out. Plus, by the end of this phase, to Jared's response earlier, you need one phase to join them, which is linear cost to R and S plus R plus S. So the total cost is simply 3 of, isn't this number looks familiar with us? That's precisely the cost of hash join, which is not that surprising. And I know the sorting and hashing, they are inherently very similar. So they lead you to the same cost. Of course, with different condition. For hashing, to get this cost, the condition is this. The condition is M over B must be greater than the smallest of the 2 partition size. Where for this refinement of so-called join, the condition is this. Okay. All right, so that's that. There is a discussion at the end about set operation, which follows very similarly to the join operators. I will skip that. You can do that yourself. And there is some discussion on general join condition, which I will skip in the interest of time. So I will not discuss how to handle, how to generalize all the algorithm we talk about for the general join condition, other than equality join. Comment there is, in most cases, for general join algorithm, for general join condition, you will use a block. That's for that. Unless you can come up with some fancy hashing algorithm that can hash your tables to different partitions where each partition satisfies a part of your join condition. Then you can do partition-wise join. Otherwise, typically people just go with block answer. Question here, then dealing. Yes.
So in simple DB, we have these operators which are DB iterators, and we have child iterators, which might come from other operators.
Yes.
But in this kind of scenario, we are relying on it coming from the disk.
I see what you mean. So
how does
this will be an operator itself. So you won't implement this using the sorting and join operator. This is the customized operator by itself. You have to implement this yourself. You cannot implement this using simply calling existing sorting operator, because if you implement this using by calling another sorting operator, by that time it's already too late. It's already sorted.
Right. So
You
does this have to be the
your-
first level, the lowest level?
Well, not necessarily. Maybe before join, you're doing a selection. Right? So you will do a selection operator before you do this. So it can be the first level, but it doesn't have to be first level. It really depends on what your query looks like. That makes sense. For example, you do a selection condition before you do join, then you want to do that selection operator first before you do this join operator. Question there?
So I guess in the general case with the cost, is it usually if you can't fit everything in memory, then the sort join or the sort refinement sort join is better. But if you can fit one of them into memory and the other one doesn't, then the hash join is better.
In most cases, people just go with hash join. Of course, it's hard to say which condition will you are able to satisfy. Is this or this, right? But in most cases, given the fact that the memory size today grows so big, the chance that this is true is very high. Basically, what you're saying, if you think about it, what it says is your table size has to be greater than the square of your memory size in order for you to not use hash join. Right? If you move this over.
Wait, isn't
Your
that
table size,
the sort join, I thought?
no, this is the hash join.
Oh.
The sort join is memory size must be greater than the total number of rounds you have from RNS, because you need one page to represent each row from RNS. Right? So the condition here, if you think about it, is if you take away the -1, your memory size, your table size has to be greater than the square of your memory size in order for you to not be able to do the hash join. Even in that case, you can still do the hash join. You just introduce a recursive partition phase. You partition that large enough partition further in order to do the in-memory hash join. Just like what we talked about for the goodbye aggregation case. Remember that? If one partition is too big, to build the rehash phase, you further partition that big enough partition. Right? Okay, all right. Now let's talk about query optimizers. Query optimization. So I'm going to motivate this using a simple example. Seeders and reserve, we talked about this many times. And we're joining them on seeder ID, and we're also employing some additional selection condition, which is bold ID equal to 100 and rating greater than 5. Okay. So this is translated to a relational algebra representation, natural join between seeder and reserve. Then after that, you do a selection, then you project out the seeder name. That's essentially your translation of this query. Okay. And this will be represented by a tree like this. You do the join operator. This actually connects to your question earlier. So in this case, join operator is at the leaf level. But you actually can rearrange the evaluation tree such that selection operator will be at the leaf level, which I will show you in a minute. So in this case, we do the join first, then we do the selection, we do the projection. Right? Now, let me give you some. So the query optimization, which you can look at these slides, but we talked about it many times. So let me quickly summarize the idea of that slide, of this slide, which is you are given an input plan like this, which is represented as a tree structure. Your objective is to optimize this plan, meaning that morph this plan into some other trees, such that the output is the same, but it's much more efficient. For example, I'm going from Salt Lake to Boston. What I would do is take I-70, merge to I-90, then I go all the way to Boston. That's probably on top of my head, that's the most efficient way of doing it. But you may have many other plans. For example, one possible plan is your goal is to go from Salt Lake to Boston, but for whatever reason you decide to drive down to Dallas, Miami, Atlanta, LA, back to LA, believe it or not, then come back to Boston. Don't laugh at it. It's still a valid plan. I take you from, if I'm an Uber driver, I take you from Salt Lake to Boston. What's wrong with it? But it's very costly, right? So the idea of the co-optimization is really given this input. Suppose that's the initial plan the Uber driver proposed to you. You say, wait. Hey, dude, don't do that. Let's go 70, 90 directly to Boston. So that's kind of the objective. But that using that simple example, 70, I-70, then I-90 take you to Boston, that's okay. But if I give you an alternative plan that's also efficient, but you end up in New York, that's not okay, because you're changing the output of your query. That's not okay, right? So no matter how efficient it is, it has to be correct first, right? So efficiency always comes second. So here we're gonna, using this example, I'm gonna motivate, why co-optimizer is important. So the big picture is like this: the query parser will generate a plan, a tree plan, like this. So that's essentially produced by this query parser. Then I'm going to go through this co-optimizer phase where I have a plan generator and a plan cost estimator. You need both. Right? The plan generator is kind of like using the example I just gave you, right? Salt Lake to Boston. The plan generator will be producing different ways of going from Salt Lake to Boston. And the plan cost estimator is to estimate the time taken by a particular route you have recommended. The naive solution is to actually drive on that route and report back what's the cost. But that defeats the purpose of optimization, right? Because if you tell me, okay, in order to estimate which is more efficient going from Salt Lake to Boston, you actually drove a route and come back tell me, oh, this, after 10 days, you say, okay, the first plan took 7 days, the second plan took only 3 days. Let's go with the second plan. That's ridiculous, right? If that's the case, I will actually do the first plan. By 7 days, I'm there. And then 10 days after, I'm still in Salt Lake. It doesn't make sense. So you have to have a really efficient way to estimate how costly a plan is. In the example I use, you use Google Maps, right? To estimate which route is more efficient, then you stick with whatever the recommendation is. But the point is, the estimation process itself must be way more efficient than actually executing query according to a given plan. And in order to do that, the cost estimator has to rely on a catalog manager that maintains your schema information and some key statistical information about your table. And this is where the black box I promised you a couple of times that we will discuss, which is selectivity estimation. I promised you many times that we will discuss that. And this is where we will discuss that. The plan cost estimator will rely heavily on selectivity estimation in order to estimate the cost of the plan. And finally, this co-optimizer box will output an optimized plan for you to execute. The execution will simply use the knowledge we discussed so far. Okay, each operator there are two things. I tell you the sequence of these operators, which one to be executed first, which one to be executed after, and in addition to that, for each operator, what's the algorithm I'm going to use? Are you going to use hash one? Are you going to use block nested loop join? Are you going to use the refinement of sort join? Are you going to use hybrid hashing for group by aggregation, or are you going to use two-phase hashing for group by aggregation? So the co-optimizer will output all of that information to you. Not only just the order of these plans, the order of these operators to be executed, but also the specific algorithm you're going to use for each plan, for each operator. Okay. Last comment here. Co-optimizer, unfortunately, in the relational model, people have proved this, that co-optimizer, to find the optimal plan for an arbitrary query is NP-hard. Which means, unless P equal to NP, we are hopeless in searching for an efficient polynomial algorithm for co-optimization. So what most systems end up doing, which is essentially the co-optimizer optimization algorithm I will introduce in this lecture, is an approximation, is a heuristic, meaning that it doesn't give you the optimal plan, but it gives you a good enough plan and get rid of those really bad plans. Meaning, for example, going from Salt Lake to Boston, I may not be able to give you the fastest route, but I guarantee you I won't give you a route like going down to Dallas, then Miami, then LA, then Boston. A really bad plan like that. I will make sure to get rid of those really bad plans. That make sense? Okay. Alright, so let's use some specific examples to look at how co-optimization might help you improve the performance of your query. Suppose these are my tables, Celer and reserve. These are my some simple statistical information about these tables. So for example, for reserve, I have 1,000 pages, 100 tuples per page, and there are 100 rows, and there are each tuple is 40 bytes long. And so similar information for Celer, and assuming we have 5 pages in the buffer group, meaning I'm over B equal to 5. So for example, in this case, B is 100. Right? B is 100 because there are 100 objects per page for reserve. So the B value for reserve is 100, the B value for Celer is 80. Right? So that's why we always use the notation B to represent that, because it is a variable. It's depending on the tuple size, object size. Right? So it's a variable. That's why we always use the value B to represent that. Okay. Now, suppose I use this plan to execute this join. And not only I give you a plan like this, I tell you the algorithm for each operator. For example, page origin natural join here. I do the selection on the fly and projection on the fly. What's the cost of this algorithm? Let's look at what's the cost of page-oriented nested join. Do you guys still remember what's the cost of this? The basic idea is you load a page from R, then you linearly scan through all the pages from S. Meaning you bring each page of S into memory, you pin that page of R, you join them. Then you bring the next page of S, you bring the next page of S. When you have finished scanning all the pages in S, you throw away that page from R, you bring the next page of R, and you repeat the whole process. Okay? Of course, it's symmetric. You can do this with R, you can also do this with S, meaning pin the first page of S, linearly scan through all the pages in R, pin the second page of S, linearly scan through all the pages in R, so on and so forth. What's the cost of this algorithm? Well, it's the number of pages in R. For each page in R, you have to linearly scan through all the pages in S. So the number of the pages in R multiply number of pages in S, and at the end of the day, you linearly scan through all the pages in R once, and also you have to plus the size of R as well. Or alternatively, if you do this with S, number of pages in S multiply number of pages in R plus number of pages in S. Since that first term is equal no matter which one you do it, so the total cost boils down to the size of the smaller relation. That always give you a more efficient plan. So the total cost is simply 500 plus 500 times 100. Why? Because there are 500 pages in Celer, 1,000 pages in reserve. So So for each of these 500 pages, you linearly scan through the 1,000 pages. At the end of it, you also will have to pay 500 pages I/O to pin all the pages in Sailor one by one. So that's the cost of this. What about the cost of selection and projection? Well, this is no cost. Why is that? The idea is so here is the memory, and here is R. There are 500 of them. Here is the S. A 1,000 of them, right? So this algorithm says I'm gonna pin the first page, I'm gonna pin this page, and I'm gonna have an input buffer to load this page, and then I'm gonna have an output buffer. I join them, and the output is dumped to here, right? Whenever I'm done with this, I will bring the next page, and whenever I'm done all of this, I will bring the second page, and repeat the process. If you pay attention to this process, whenever you find a joint pair, so they are output here. What you do is, you don't keep this pair of records unless they also satisfy your selection condition. That's what I mean by doing this on the fly. Furthermore, you don't keep the whole thing, you keep only the projection part of this pair of records. If they satisfy your selection condition. So you do both selection and projection on the fly. So they introduce no additional IOs, and introduce no additional cost.
So is the projection in the plan, it's projection without duplicate removal?
If you don't have very good question, if you don't have distinct keyword in the SQL, we modify the semantic of projection operator here. It does not remove duplicates.
And that's why it doesn't have extra costs.
Yeah, that's right. Any questions so far? So the total cost is about 500,000 IOs. Can you do better? Well, you're gonna say, okay, I'm gonna push down the selection operation. I'm gonna do the selection on the fly. So what this means? This means, look at what we're doing here. I'm gonna erase all the other things so it's better for you to focus. Okay? Easier for you to focus. If you really think about what we're doing, while I'm pinning this page from disk to memory, you're loading this page to the memory anyway. What about right after you have loaded to memory and before you load anything from the other side? You pause this, and there's nothing in the output buffer. You have a page of data. At this point, you apply your selection condition over this page of data. What's the effect of that? The effect of that is you will end up with less than a page of data. In most cases, unless you're really unfortunate, you're really unlucky, your selection remove no records whatsoever, which is typically not the case. Again, it boils down to the selectivity of your query, right? Do you follow me? Now, assuming in our case, we assume that there are 10 different rating values from 1 to 10, and if we further assume that they follow a uniform distribution. Can someone tell me what's the selectivity of this query? 50%. There are 10 different rating values from 1 to 10 and uniform distribution. What's the selectivity of this query? 50%. right? 50%. What that means is I expect to say one page of data becomes what? Half page of data. Generalizing this argument, how many pages of data from R you can pin to this input buffer at a time? 2. Every time you can pin 2 pages of data into this input buffer, because 2 of them after applying this selection operator will become just 1 page of data. Every 2 pages of data on average is reduced to 1 page of data. Do you follow me? And if you look at what the plan says you do this on the fly, then you do page-oriented nested loop join. Page-oriented nested loop join means that you only start the looping process after you have a page of data. Means that after pinning 2 pages, you have a 1 page of data. Now you resume with this linear scanning process, going through this and to the output buffer. And you do the other selection and production still on the fly. That's no problem. So what do you expect the cost to be in this case? Looking at what we're saying. Well, it's become, instead of doing 500 times 1,000 loops, you are doing only half of this many loops. But at the end of the day, you still need to scan through all these pages once, so the cost becomes this. Do you follow me? So about half. So simply pushing down an operator, a selection operator, reduces the cost by half. That goes back to my earlier response to you. Sometimes you don't want to join operator to be your leaf level. Right? In this case, join operator is your leaf, but sometimes you want to push down a selection operator to be your leaf. Do you follow this argument? Okay, you may wonder, okay, fantastic. If this selection pushing down reduces my cost by half, what about pushing down the other selection to the other side? First of all, what's the selectivity of this query? Remember, the condition is we have 100 distinct bolts. Again, let's assume the reserve of different bolts follow a uniform distribution, meaning roughly each bolt receives the same number of reservations. We have 100 bolts. You are selecting one particular bolt. What's the selectivity of this query? Sorry, not this query, this selection condition. What's the selectivity of this? 1%, 1 over 100. So if I push down, following the same argument, my cost should be roughly this, right? Divided by 100. Right? But it's not. What's the cost of this, actually? Surprisingly, it has no effect. It's simply still this. Why is that? Someone tell me why a reduction of 100-fold? It's very counterintuitive. Right? I have a reduction of 100-fold, yet it has no impact to my query cost. That's weird. Go ahead.
Let's say you have to do the reduction for every page, not in the same order.
Exactly, and by that time you paid I/O already.
Yeah.
It's too late. Precisely. So what happened is, yes, this is still the case, right? You are still pinning every 2 pages into a page. This part stayed the same because you did push down that selection on reading. While the selection on bold, what happened is, yes, 100 of pages, this is 100 pages, reduced to just 1 page. This 100 pages reduced to just 1 page because of that selectivity of 1%. But by the time you have reduced them 100 pages to 1 page, you have to look at these 100 pages. You pay those 100 IOs already. You're still looking through all the pages. So it's still this cost. You save nothing in terms of IO cost. Yes, you did save then in memory you still save the cost of doing this by 100-fold, but not the I/O. Not the I/O.
Sarah, couldn't you just save that page?
But that's not what the plan says.
Okay, right,
Plan
right.
says on the fly.
But if you reverse the situation, like first
Yes.
take from the right and
Yes.
convert all the left ones,
Excellent.
then
That's exactly what I will do. That's exactly what I will do. If I'm inside the CPU and I can control how the CPU does things, and that's exactly what I will do. And my cost will be 10 times, because 10 is 1,000 divided by 100. But at the end of the day, I still need to linear scan those 1,000 pages, meaning I swap the position of the two. That's exactly what I will do, and I will reduce this to 6,000 IOs. So we start from 500,000 IOs, we're down to 6,000 IOs. And what about what Jared said? Don't do this on the fly. Dump to disk and do it again before you bring them to memory. It sounds, again, very counterintuitive, because doing this on the fly seems like always better than dumping to disk and bring back to memory again, because you are introducing additional overhead if you do that. But not necessarily always that's the case. I'm going to give you exactly what Jared recommended. So combine what both of them have said. Meaning I do this on the fly. I do this, I push down the selection. If I do this on the fly, then this will be exactly the same like that. There's no effect, other than reducing the in-memory join cost. But the I/O cost is the same. You follow me? But what I'm going to do is I'm going to scan and apply this selection and dump to disk before I do the join. So what the picture looks like. Well, the picture is going to look like this become my so 1,000 pages become just one page. Sorry, 100 pages become just one page. And my memory, I'm gonna shrink my memory a little bit. So I'm gonna read every 2 pages and dump to just one page. But I dump to disk. So every 2 of them will be reduced to one page. So at this point, how many pages I have here? I no longer have 500 pages, I only have 250 pages. So my cost become this, plus 1,000, reading through, and of course, you have to read out 500 pages and write 250 pages. You load all of that, 2 of them become 1, you dump to disk. Instead of doing this on the fly, that's why you have this cost. Seems like this is additional overhead. However, because of that overhead you pay, you end up doing much less number of loops compared to on-the-fly solution. So, much better. And you can, of course, flip 2 of them and do the other way. Cost you better. And there are more alternative plans. I will stop here. I will continue on Thursday. But the point is, CrossMatter can do a lot of tricks for you. There are many alternatives. Okay? And the challenge, of course, is how do you do this using a computer algorithm? Of course, if I can shrink you small enough to a molecule size, I can push you to the CPU and do this, but that's not possible, right?